We are again going to talk about solid solutions alloys in this lecture 18, continuing from where we were in the last lecture. So in the last lecture we said that when you put an impurity in a material, the impurity may go to either substitutional site or interstitial site. If it goes to substitutional site, it makes a substitution solid solution, and if it goes to interstitial site, it makes an interstitial solid solution, and where it goes is determined by the size. Okay. So there are some rules for substitution solid solutions which were called as Hume-Rothery rules. Okay. So Hume-Rothery rules, which said that depending upon the size difference, depending upon the valence difference. So if you want to make a substitutional solid solution, extensive solid solubility is permitted only when the size difference is less than 15%, when the valences are nearly similar or similar, crystal structures are similar, and electronegativity difference is very small. There are certain violations, but by and large these rules are followed. So the examples which we took were gold, silver, silicon, germanium, and copper, nickel. These are solid solutions basically. So if you look at, for example, what I mean basically here is, if you look at the phase diagram of silicon germanium, so this is composition axis, percentage germanium from 100% silicon to 100% germanium. This is temperature axis. Okay. So silicon has a melting point, let us say some Tm silicon, which is nearly 1400 degrees centigrade. This is germanium melting point, Tm germanium, and what they basically form is a structure which is all throughout the same structure. So this is basically, let us say it is a silicon germanium alloy which is solid solution. So it is basically a disordered solid solution, it is not an ordered solid solution. So at this temperature it is liquid, between this it is liquid plus solid, and here it is liquid plus only solid, and this solid is this solid solution. Okay. So at 0% germanium it has a structure which is FCC structure, at 100% germanium it has a structure which is 100% which is FCC, and intermediate phases also have, intermediate compositions also have FCC structure all throughout. It is happening within the same structure, same lattice. It is just that some of the silicons are being replaced by germanium. If you move from silicon side, if you move from germanium side, some of the germanium atoms are going to be replaced by silicon. So even at 50-50, it is 50 germanium, 50 silicon, with each atom having a probability of being 50% germanium or 50% silicon, each site occupancy. So this is a disordered solid solution which shows extended solid solubility. So this is true for gold, silver, this is true for silicon germanium, this is true for copper, nickel. What happens in partial solid solubility is slightly different. So in partial solid solubility, I will not draw the complete phase diagram, but let us say you take an example of A and B. This is 100% A, this is 100% B, and you go, this is percentage B. And on the left side, on the vertical axis, you have temperature. Okay. Now, what happens in partial solid solubility is that, so solid solubility typically increases as the temperature increases. So this line determines up to which point in composition space the solid will dissolve. Similarly, on this side, you will have these boundaries. So between this and this, it will be, let us say, alpha phase. Alpha phase is solid solution of B in A. So basically it is A with some of the A atoms replaced by B. This is beta phase. This is basically solid solution of A in B. Essentially it means it's nearly B with some atoms replaced by A, and this is a substitutional solid solution, which is a disordered solid solution, disordered substitutional solid solution. Between these two things, it gives a mixture of alpha and beta. This is one simple example. There are more complicated examples where some other phases may form and so on and so forth, but this is one simple example of where solid solubility is limited. Let us say at this point it is 10%, at this point it is 5% or some other percentage. It increases as you increase the temperature. Typically solid solubility increases as the temperature is increased. Okay. So, because the lattice dilates and there are other thermodynamic factors, the competition between entropy and enthalpy, eventually that determines what the solid solubility will be, but this boundary is the boundary beyond which you cannot add any more B to A. If you add any more B to A, so up to this point at a fixed temperature, let us say this is room temperature. So, if you keep adding B to A, it will remain in the structure of A up to this point. Beyond this point it will form beta phase. So, as soon as you cross this point, it will start converting into alpha plus beta, and this alpha plus beta will continue to remain in existence until you reach this point. Proportion of alpha and beta will change, which will be determined by lever rule. If you know the phase diagrams, the proportion of alpha and beta will change in this regime, but you will have two phase coexistence because the solid solubility of alpha and beta are limited. So, this is the limit of solid solubility of beta, this is the limit of solid solubility of alpha, and this happens when you have departures from Humo 3 rules, when the size differences are larger, when crystal structures are not similar, when valences are not similar, and when electronegativity difference typically gives rise to formation of compound, but these are the factors when. So, this is, you can say, the departure from extensive solid solubility. So, this is the case of, as we say, limited solid solubility. Is that clear? Yeah. So, this is what happens in most cases. So, as I said, in case of copper, zinc, you can have 35% zinc in copper, and in case of zinc you have 1% copper in zinc. So, you can see, if now you can correlate to the previous diagram, that on the copper side the boundary can extend up to 35%, but on the zinc side it can extend only up to 1%, and this is because copper and zinc have different structures, they have different valences. So, that is why. And so when you mix two elements, sometimes, as I said in copper zinc example 50%, you have ordering. Okay. So, in case of copper zinc, what happens is that, so when you add 35% zinc, it remains as FCC. When you add up to 1%, it remains as HCP. But in between, as I said, it starts forming other phases which are different. So, for example, you had BCC fade in between, okay, or you had simple cubic phase in between, depending upon the temperature. So, you no longer have FCC HCP structured phases, you have some other phases. These phases are basically formed because copper and zinc tend to form secondary phases. So, especially at lower temperatures, when you mix two elements, they tend to arrange themselves in ordered fashion. So, this is called as ordering in alloys. So, as I said, at lower temperature it had a ordered structure. Okay. So, this ordering in alloys it happens in solid solutions. Typically at lower temperatures due to free energy changes. Okay. And this is mainly determined by delta H, which is dependent upon the nearest neighbor. Enthalpy is determined by the nearest neighbor interactions, because its enthalpy is a manifestation of bond strength, and bond strength is a manifestation of nearest neighbor. What is the configuration? Copper zinc bond will have different bond energy, zinc zinc bond will have different bond energy, copper copper bond will have different bond energy. So delta H, and then you will have delta S, which is predominantly configurational entropy, which is given as delta. So S, you know, is given as K ln W, where W is the number of ways in which arrange two atoms. So when you mix A and B, you can arrange A and B in number of different ways. So find out, so you calculate various permutation combinations, then you calculate the configurational entropy. So you then, so after that you do delta G is equal to delta H minus T delta S. So at a fixed temperature, work out what is free energy, and at a given temperature whether you will have a disordered structure, ordered structure will be determined by minimization of free energy at a given temperature. Usually at high temperatures, random arrangements are preferred. Okay, typically, and lowering of temperature leads to ordering, which is mainly determined by lowering of enthalpy. Enthalpy is lowered, as a result your ordering takes place.
We can also say that ordering is also a function of concentration.
It's also a function of concentration. Not every concentration will give you ordered alloys. That is also true. But typically we talk in the context of fixed compositions. So we take a composition and then we see whether it's ordered or not at a given temperature. But yeah, I mean, not every composition is ordered. So it's also thermodynamic variables are temperature, concentration. So these are thermodynamic variables. Of course, pressure is also thermodynamic variables, but in most metallurgical processes, pressure in these kind of processes, at least pressure is kept as a constant. Okay. So yes, temperature and concentration both are variable. Here we were talking of fixed composition, but of course if you change the composition, you will have to change the whole thing altogether in that, and you may find that there is something else which is happening there. Okay. So there are, so ordered alloys in case of alloys, metallic alloys, they are often called as intermetallics. These intermetallics are strange compounds because they have very fixed composition. If you go slightly away from the composition, they will decompose into something else, or they will be present in a two-phase mixture where this particular compound will be present or something else. So let me draw a phase diagram, for example. AB, let's say. Let me see if I can. this is temperature. So, this is on this side you have. So, this is alpha phase, this is beta phase, this is liquid, this is liquid. The temperatures may vary. So, this is liquid plus alpha. This is a compound which is, let us say, AB compound or AXBY compound, which is intermetallic compound. So, this is liquid plus AXBY, this is again liquid plus AXBY, and this is liquid plus beta. On this side you have alpha plus AXBY, here you have beta plus AXBY. So, you can see that at this particular composition, which is let us say AXBY, you have a fixed composition. If you are standing at this composition, you are in two phase regime where you have alpha plus AXBY. You can see that the solid solubility of alpha is changing as a function of composite temperature. The solid solubility is moving towards right as you increase the temperature. Similarly, solid solubility of beta phase also, it is not drawn very neatly. Let me just probably draw it a little neatly. So, this will be 100% B, and this is so this is let us say alpha C alpha, this is let us say C beta. Okay. So, solid solubility is increasing as you increase the temperature of alpha, solid solubility is increasing of beta as you increase the temperature towards the left, this is beta phase. So, at this temperature, if you compare these two temperatures at T1 and T2, at T2 alpha has more amount of B than at T1, right. Similarly, at T2 beta has more amount of A than at T1, is that right? But you can see AXBY, this remains vertical. The composition of AXBY does not change, it is a line compound, it remains fixated. When you are some other composition, you have alpha plus AXBY, alpha of this composition, AXBY of this composition, but composition of AXBY will remain same if you were, for example, at this temperature. So, if you keep the composition fixed, go to this temperature, at this temperature again you have alpha plus AXBY, but composition of alpha has changed according to this composition. So, at this temperature alpha had a composition of C1, at this composition alpha has a composition of C2, but AXBY has same composition all throughout. This is a line compound, which means it has a fixed composition and it forms only at that particular composition. So, in two phase alloys, you will see at a composition you will have two phases, one of them may be line compound, another. For example, cementite, as we see in steel. Cementite is a fixed composition thing. Okay. So, in steel, that is a very good example actually. So, if I draw the phase diagram of steel, this is iron, this is carbon. So, steel has a eutectoid reaction. I will only draw the low temperature reaction. Okay, I will just draw the. So, this is alpha, this is alpha plus gamma, this is gamma plus Fe3C, and this is alpha plus Fe3C. Fe3C cementite, whose composition is given by this line, is a fixed composition. So, Fe3C, as you change the temperature, so if I am at let us say 0.5% carbon steel at temperature T1 and at temperature T2, I have alpha and Fe3C in both cases, but here alpha has a different composition, which is this, Here alpha has a different composition, which is this. So this is number 1, this is number 2. But Fe3C has same composition, which is determined by this vertical line, which is Fe3C. It's a line compound. Its composition cannot change because composition is 3 iron, 1 copper, 1 carbon. 3:1 ratio has to be maintained. So this is a line compound or a intermetallic compound. Okay. So basically intermetallics are compounds of fixed composition typically they don't have any variation in the composition and they are called as line compounds. The examples are first one is Fe3C or cementite in steel. A lot of times you have this Ni3Al nickel aluminum system. Ni3Al is very, and another thing is that these line compounds are very strong. They have much higher strength, higher hardness and strength over host lattices. So for example, in case of Ni3Al, Ni3Al has a yield strength which is of the order of 850 MPa. This is nearly 5 times more than of stainless steel SS. And aluminum is, if you look at the composition, aluminum is a soft alloy. Nickel has a strength which is of the order of iron, steel. But Ni3Al, the line compound is very strong. Similarly, cementite in steel is extremely hard. It's very hard. Very hard. That is why we prefer high carbon steels for application which require high hardness, and this high hardness comes from cementite. And similarly, you have things like Cu3Au. These precipitates, they form in copper gold systems, and they again give rise to high hardness. So copper gold. Similarly, there are a lot of other systems. You have things like CuAl, I showed you CuZn. So all of these intermetallics of fixed composition, they have high hardness. And then, so for example, Ni3Al again, so Ni3Al, when it is disordered, then this is nickel is FCC, iron is FCC, aluminum is FCC. So when it is disordered, then each atom can be considered as 75% nickel and 25% aluminum in disordered form. This is Ni3Al. When it is ordered, then it is different. In case of ordering, this is nickel, sorry, this is, let me draw all the 6 atoms. This is ordered structure. So here what is this? Nickel, and this becomes, so this is ordered Ni3Al, where nickel goes to half 0, half 0 half and aluminum goes to 0 0 0. So this is a FCC lattice, and what is lattice? What lattice is this? FCC lattice with motif at 0 0 0, and this motif is basically 75% nickel and 25% aluminum. In this case, it is simple cubic. Right, and simple cubic with 4 atom motif. So this is the motif, 4 atom motif. And this Ni3Al is very useful because it's used in superalloys as strengthening, to strengthen the superalloys. Nickel based alloys are superalloys, and this, if you add some aluminum to nickel, they form Ni3Al precipitates, and these precipitates provide resistance to dislocation motion, and they make the nickel alloys stronger for high temperature applications. Then there is another category, last category I will say, is called as electron compounds. These are the compounds which do not obey the rule of valency. So don't obey the valency rule. They occur at certain electron to atom ratio, and these ratios are typically 3:2, 21:13 and 7:4, and they are formed in same system. For example, CuZn could be beta CuZn, Cu3Zn2, gamma CuZn, Cu5Zn8, sorry, this is not Cu3Zn2, this is CuZn, because valence is, copper has 1 valence and zinc has 2 valence. So the valence is, electrons are 3, atoms are 2. Here 5 into 1, 8 into 2 will make it 21, atoms are 13. And then third one is epsilon CuZn3, which has 7:4. So this is 3:2, this is 21:13, and this is 7:4. So these are called as electron compounds. So what basically we have looked at is various type of compounds, line compounds, electron compounds, solid solutions, how they follow Hume-Three's rule, and why solid solutions form, and what are the guidelines. Finally, if you want to calculate the theoretical density of a material, it is given as Na divided by VCNA, where N is the number of atoms per unit cell. This is atomic weight. Vc is the volume of unit cell, and NO is the Avogadro number. So by this you can determine the atomic density of metals. Okay, so this completes our metals and alloys chapter, and we will in the next class start the covalent and ionic solids. Thank you.